So this is the second lecture on statistics for particle physicists. And Glenn, it's all yours.
Thank you very much, Albert. Let's see, I just hear that my cat in the background is making a tremendous noise, so just ignore her. She's and let's get started. Let's see, why can't I? Last time we were talking about parameter estimation, and I wasn't quite finished with what I wanted to say. Let me see, is my video on? It should be, isn't it? Yeah. So I'd like to finish up with what I'll call the graphical method for determining the variance of a maximum likelihood estimator. That'll be very quick. And we'll go on to the main topic for today, which is hypothesis tests and setting limits, very important pieces of technology for particle physics analyses. So in the last lecture, we were talking about the minimum variance bound of an estimator. Let me try to move this down. And you will recall that we said that the variance, let me try to see if I can write it in here, the variance of any estimator for a parameter theta that had to be greater than or equal to this thing that we call the minimum variance bound. And that was given by minus 1 plus the derivative of the bias with respect to the parameter 1 plus that, the quantity squared, all divided by the expectation value of the second derivative of the log likelihood function with respect to the parameter. And then furthermore, we said that this inequality is an approximate equality in this large sample limit. So that was the so-called information inequality. And what I want to do now is to use that information inequality in the approximation where it is an equality in order to find a procedure for determining the standard deviation or variance of a maximum likelihood estimator in a graphical form. And the way we'll do that is to take the log likelihood function and expand it in a Taylor series about the maximum likelihood estimator. So if we said that log L is equal to log L of theta hat plus then a first order term and a second order term, and let me stop at second order, right? So let's see, that first order term there, that's just the maximum of the likelihood by definition. Theta hat is the value of theta that maximizes the likelihood. And since I'm at the maximum, then the derivative at the maximum is 0, so that term is 0. And then in this second order term, I have the second derivative of the log likelihood function with respect to the parameter. And I can relate that to my approximation for the variance using this minimum variance bound. That is to say that to the extent that I can approximate the expectation value of the second derivative term by the value of the second derivative just evaluated at its maximum. Right. Now, if this log likelihood is approximately just described by a second order polynomial, by a parabola, then its second derivative is constant. So the expectation value will be then well approximated by this second derivative at the peak. All right, so let me take this Taylor expansion now and rewrite that as log L is approximately equal to log L max. And then what I've done here is I've replaced this second derivative term by the corresponding minus 1 over then the variance of theta hat, right? So that's interesting, all right? That says that the log likelihood function in the neighborhood of the peak can be just approximated by this parabola. And if you consider moving theta away from theta hat by plus or minus 1 standard deviation, right? Then what that means is that the theta minus theta hat squared in the numerator cancels the variance in the denominator. And it says that moving theta away from theta hat by plus or minus 1 standard deviation simply causes the log likelihood to decrease from its maximum by 1/2, right? It's that factor of 1/2 that's left over. And so that's the recipe. The recipe says that if you look at the log likelihood near the MLE, all right, it's approximately parabolic, and you come down from the maximum by 1/2, and then you project that distance down, or it should be symmetric, you could do it on either side, then the distance that you move theta away from theta hat in order to get that decrease is 1 standard deviation of theta hat. And that's the number that you would report as the statistical error in your estimate of theta. All right, so that's the so-called graphical method for the case of a single parameter. And I have it's in the extra slides from the first lecture. There's some generalization of this to the multi-parameter case as well. But now let's first look at it at a quick example. We had talked last time about this example of an exponential distribution. And so here is then the log likelihood function from that example. You'll have to refer back to the first lecture for the details, but that's the log likelihood function. It has a maximum here at the value that we call tau hat, the MLE. You come down by 1/2 from the maximum. And so you can see that it's not quite symmetric to the right and to the left. Let's see, if you go to the left, that distance is 0.137. If you go to the right, the distance is 0.165. So now what do we give for our estimate of the standard deviation? Well, it would be legitimate in this case to do something simple and just say average those two and say that my estimate of the standard deviation of tau hat is 0.15. Now, the standard deviation is a single number. There's no such thing as a left standard deviation and a right standard deviation. So it's one number. Nevertheless, there can be circumstances in which it's meaningful to report a sort of asymmetric error bar. You would give your answer as tau hat and then plus, that distance to the right minus that distance to the left. So you give a sort of asymmetric error bar. That procedure can be interpreted as defining what we call a confidence interval. And I will describe that, I will define that more accurately later on. Right. Remember, we said that this log likelihood function becomes parabolic in the large sample limit, but in this Monte Carlo sample, it was just with 50 observations of the random variable t, so it's not exactly parabolic. You can see already the departure from the asymptotic case. All right, that was all by way of finishing up from last time. I hope that didn't take too long. I think we're okay. So let's go on now to the main topic of today, and that is hypothesis tests in the frequentist framework. All right. And so what's the setup? Let's suppose that we're doing a measurement, and the measurement results in some vector of data that I'll call vector x. Right? It could be a single number, it could be a large collection of numbers. Now let me consider a hypothesis H0 that I want to test. And I also want to consider an alternative to H0 that I will call H1. Now remember that when I say a hypothesis, what that means is that it specifies the probability for the data. So when I say consider a hypothesis H0, that means that I have in mind some rule that assigns a probability to every point in X space under assumption of this H0. And similarly for H1, that implies a different rule, a different probability. So how do we define then a test of H0? What we do is the following, is that you specify a subset of the data space, which is called the critical region. And the defining property of this critical region is that there should be some small probability that we call alpha to find the data in that critical region under the assumption of the hypothesis that we're testing. So the defining property is the probability to find X in the critical region under the assumption of H0 should be less than or equal to this value alpha. Alpha is what we call the size of the test. And it is some conventional constant that you choose before doing the test. It's formally small, so you might choose some value like 5% or 1% or some small value, but you assign its value before doing the test. Now, normally I would actually like this inequality here to be equality. I would like to find a critical region such that the probability to find the data there is equal to alpha. Now, that might not be possible if the data involved are discrete. So if you're counting, say, a number of events, you might, for example, under the hypothesis in question, have I don't know, a 4.5% probability to find 0 or 1 events, but a 5.2% probability to find 0, 1, or 2 events. And so you might not have any particular subset of the data that gives you exactly 5%. Suppose you want alpha equals 5%. If that's the case, what you do is you choose the critical region to include as large a region of the data space as possible under the constraint that is less than or equal to the assigned size. Okay, so yes, alpha is called the size. Sometimes it's called the significance level of the test. Usually I'll use the term size. All right, so just symbolically, fine, there's the full data space. Critical region is some subset of it. And then you do the test. How do you do that? That's very simple. You simply observe X. X will fall somewhere in the data space. And if that happens to be in the critical region, then you reject the hypothesis. So the outcome of this type of frequentist hypothesis test is a binary statement of the form reject H0 or not. All right. That might sound a bit incomplete because you might think, well, hang on, how did you know where to put the critical region other than just from this requirement? Because after all, I might have put it over here. There's many, or perhaps in general, an infinite number of possible choices for the exact place of the critical region. Just specifying that it contains, say, 5% of the probability, that doesn't seem sufficient. That is where the alternative hypothesis comes into play. All right. The alternative hypothesis is what we use to motivate where to place the critical region. And roughly speaking, the rule is that you place the critical region for the hypothesis of H, for the test of H0, such that there's this probability alpha to find the data there under assumption of H0. But you want as large a probability as possible to find the data there if this relevant alternative, H1, is true. And so here, let's just suppose that X is a single quantity so that I can sketch it, all right? And let's suppose that the PDF for X under the assumption of H0 is this curve on the left. And then the curve on the right, that's the f of X given H1. And I want a test of some size alpha, say 5%. And so you can see that the probability content of X, of this f of X given H1, that's concentrated further off to the right. And so therefore, I would place the critical region W on the right, such that there would be like an upper tail area of alpha under the curve f of X given H0. And then you can see that there's a much larger area under the corresponding curve for H1. So the area under the curve in the critical region for the alternative, that's what's called the power of the test with respect to H1. It is a test of H0, and this is the power of that test with respect to the alternative H1. Sometimes I use the letter M for the power. The letter P is way overused because we've already used that for probabilities of various sorts. So in any case, use M for the power. Okay. Now, let's just explore this a little bit further. And here's a context in which this could occur in particle physics. Let's suppose that we're looking at events, and they come in two possible types. So these are going to correspond to two hypotheses. Signal events, called S, and background events, B. And for each event, I want to carry out the test. So the data that I'm considering is the data that pertains to an individual event. All right, so I'm going to carry out one of these hypothesis tests for each event, and I'm going to test the hypothesis H0 that it is an event of the background type. Now, let me just comment that in frequentist statistics, we said that we wouldn't associate necessarily a probability with a hypothesis. We only associate a probability with the data. We only associate probability with the outcome of a repeatable observation. But in this type of a context, you can imagine that the label of the event, signal or background, that is a label that varies randomly upon repetition of the observation when you observe more and more events. So I can also associate a probability with the hypothesis in this case with the probability that it's a background event or the probability that it's a signal event. And so what you can imagine doing in this context is to carry out this type of a hypothesis test for every event that you look at. And then if you reject the hypothesis H0, that it is an event of background type, then you'd set it aside in your collection of candidate signal events. Right? So in other words, rejecting it as background means that you select it as a candidate signal event. And so in that context, the corresponding particle physics terminology would be, let's see, here's the size of the test. That's the integral of the PDF assuming H0 over the critical region. And that's the region where you reject the background hypothesis. So you'd select the event as a candidate signal event. And that in a particle physics context is usually called just the background efficiency. All right, so the background efficiency corresponds to the size of the test. On the other hand, if you do the corresponding probability for background, so H1, that's signal, right? And H0 is background. Then if you're in the critical region, it means that you've rejected the background hypothesis, you've selected it as a signal event, and so that's the signal efficiency. And so that corresponds to the power of the test. All right, so anyway, that's just the correspondence then between the statistics terminology and the particle physics terminology, at least for this type of a problem. And remember that in this game, I've defined it so that the hypothesis that we're testing is B. Right. All right, so here's an example. Let's suppose that for each event, I can measure a quantity X, a single quantity. And let's suppose that X is distributed for signal events according to this PDF here. It's the red curve. Okay, I've defined X so that it lives on the interval between 0 and 1. And normally I wouldn't have such a simple analytic formula for this distribution, but let's suppose that in this example, I know that F is distributed according to this falling red distribution. And that for background events, let's suppose that X follows the blue curve here. All right, so it's concentrated more up at high X. And so for each event in a mixture of signal and background events, I want to test the hypothesis that the event is of type background. Now you can see that where do I choose the critical region? Well, the alternative is peaked over on the left. And so therefore, that's where I put the critical region. Right? So it has a probability alpha under the assumption of the background hypothesis. And then I'd get a much larger probability in that same region under the assumption of the signal hypothesis. So the critical region is the set of X values such that X is less than or equal to some cutoff value, X sub C. So we're going to choose X sub C to get a test with the desired size alpha. All right, so you can tell how to determine then X sub C. Let's suppose that you wanted a particular alpha, so you want a background efficiency of 10 to the minus 4. And so that means that the criterion that determines the edge of the critical region would be that to say alpha is equal to the probability to find the data there under the assumption of B. So you just integrate that PDF, all right, and you get XC to the 4th there. And so you can solve then for XC and you get 0.1. All right. And just as an example, then we can work out the power of this test. The test is defined then by this critical region, right? And then the power of that test with respect to the signal event hypothesis is found by integrating the signal PDF over that same critical region. And you get some number which is 0.19. So that's the probability to find the data there for a signal event. That would be the signal efficiency. Whereas the background efficiency is much lower, 10 to the minus 4. Now, you might ask, how did I know that I wanted a background efficiency of 10 to the minus 4 and that you wind up with a signal efficiency of 0.19? Isn't there some possibly different balance between the two? Yes, the optimal size of the optimal values for the size and power, which is to say signal efficiency and background efficiency, that's a separate question that will depend on the goals of the analysis that you're doing. I'll just point out that you can see that there's a trade-off, right? If you want to have a large signal efficiency, it means you're going to also have to have a large background efficiency. All right. All right. So let's go on. That was just an example to illustrate how this game works. Let's suppose now, to exercise this example a little bit further, let's suppose that the prior probabilities in this mixture of events for an event to be a signal event is 0.001. And so it's a 0.999 probability to be a background event. You can imagine that this is something like proportional to the cross-section for the signal process. And this is proportional to the background cross-section. Sorry, B sigma B, right? So from these cross-sections, then you, well, it's basically sigma S over sigma S plus sigma B, right? That gives you the prior probabilities. So suppose we want to know then, I've tested each event. I've tested the background hypothesis for each event. If that's rejected, I have it set aside in my candidate signal sample. Amongst that signal sample, I want to then ask, what's the probability that the events really are of the signal type? So I want to know the probability that an event is of type S, given that the background hypothesis was rejected, given that it landed in this critical region. So you can see I have there a conditional probability with the S on the left and the critical region on the right. And I can use Bayes' theorem to relate that to the corresponding probability to find X in the critical region, given that the event is of type S. And Bayes' theorem says that this is the formula, right? It's the probability to have the data in the critical region given S times the probability to be, the prior probability to be S, divided by the corresponding probability to be in the critical region, which I have written out with the law of total probability in the denominator. And so, of course, I have all of these ingredients, right? Because the P of X in the critical region given S, we've worked that out. That's the power of the test. And P of X in the critical region for B, that's the size of the test. So I have all of these numbers, and you can work out what you would call in particle physics the signal purity. That's for all of the events that you found in the critical region. And there's a related question, which might be the following. Let's suppose that you had an individual event observed at a specific value of X, and you wanted to know what is the probability that that individual event is a background event. So then again, you can use Bayes' theorem, but instead of having the probability to land in the critical region, what you would put is the PDF evaluated at the value X. All right, so we can also work that out. And that would say that in this particular example, being at X of 0.1 would give you a certain probability, 0.689, that individual event, here I've worked it out to be a background event. Okay, so that has nothing to do with this test in the critical region. It's just an illustration of Bayes' theorem. All right, I hope that wasn't too rushed. I hope that made sense. That was just to illustrate the notion of a critical region and the concepts of size and power. Let's go on. In this example that we just looked at, X, the data, was a one-dimensional quantity. It was a single number. But and so choosing the critical region was fairly trivial in that it was just the values of X less than some cutoff region, or so X less than X cutoff. What do we do if the data space is multidimensional? Then it becomes less obvious where to choose the critical region of the test. How can we do this in some sort of optimal way? Well, it turns out that there's a theorem that tells you the optimal critical region in a specific sense, which I have to now define. And this is what's called the Neyman-Pearson lemma. And it says the following. It says that for a test of a hypothesis H0 of a given size alpha, then in order to get the highest power with respect to a specific alternative H1, then you need to choose the critical region such that it has the following property. For every data point, for every X point inside the critical region, then this inequality should hold, the probability of x given h1 divided by the probability of x given h0, that should be greater than or equal to a specified constant everywhere inside the critical region, and it should be less than that constant everywhere outside. And then it's equal to that constant on the boundary. And the value of the constant itself that I've called C alpha, it is chosen to give a test of the desired size. All right, so that's why I've put the subscript alpha there. All right, so if you imagine here's your multidimensional data space, I don't know, xi versus xj, just to sketch 2 dimensions, then there will be some surface here, and that surface will be described by a particular function of x equal to a constant. Namely, it's going to be that ratio equal to C alpha. That equation is going to define that surface there, which is the boundary of the critical region. All right. So that function of the data that defines the boundary of the critical region, I'm going to call that a test statistic. All right. And so that is what tells me then the optimal test statistic. So, right. And that gives me the optimal critical region in this sense. It gives me then the highest power for a test of a certain size. But I have to then specify an exact alternative. And I'm testing a unique null hypothesis H0. And so you would then say select the, you would say that the critical region is defined by, I have to make sure I say this right, sorry. Yes, so the critical region then is going to be defined by the set of x values such that x, sorry. The critical region will be defined by having T of x greater than or equal to C alpha, where this T of x is this ratio of probabilities. And this ratio is what is called a likelihood ratio, right? Because both the numerator and denominator here, this is the likelihood of hypothesis H1 divided by the likelihood of hypothesis H0. So that defines, that equation of that form defines the critical region. I want to point out that the any monotonic function of this ratio would be equivalent for use as a test statistic. In other words, if I were to say that the critical region consists of the region of X space where, say, T of X is greater than C alpha, then that's the same region, say, where the log of T is greater than the log of C alpha. So any monotonic function of this likelihood ratio will lead to the same test. And I mention that because occasionally this comes up. We will use, say, the logarithm of the likelihood ratio and say that that leads to the optimal critical region. All right. Now, that seems to have said that we've solved the problem. We've determined exactly how to set up every possible statistical test, every possible hypothesis test. The problem is the following, is that in practice, we often do not have explicit formulas for the PDF of the data for signal events and the PDF for the data for the background event. So if you give me a particular event at a point X in X space, I can't actually evaluate this statistic. So I can't tell you whether that point is in the critical region or not in the critical region. And you might be saying, how can you not have these PDFs? After all, you've said that you know what you mean by a background event, you know what you mean by a signal event. How do you not have the PDFs? Well, recall that in particle physics, what we typically have are complicated Monte Carlo models for the signal process and for the background process. So we can generate points in X space for the signal events, and we can generate X values, events for background, right? And that would give you samples of simulated signal events and simulated background events. But that doesn't mean that you have a closed form expression for this formula. right? You start with some complicated, with some set of formulas in the Monte Carlo model, and then you go through some very long sequence of steps before you wind up generating, say, the momentum vectors of the particles that constitute the final event. So that means that the Neyman-Pearson lemma doesn't usually help in practice. We can't actually construct this likelihood ratio in many problems of practical interest. But what we can do is the following, is we can take these generated event samples and we can use those to try to find a statistic that is as close as possible to the optimal likelihood ratio. And that leads into this field of machine learning or multivariate analysis. And that would be a completely different set of lectures. And so I'm not going to go into that now. But that is just to say, it's important to realize that there is at least a piece of mathematics that tells us what the optimal goal is. The best critical region or the best test statistic will be determined by something like this likelihood ratio. And what we can use are machine learning algorithms to try to get as close to that as possible. All right, let's keep going. That's the basic type of hypothesis test that I wanted to introduce, where you have a critical region and there's a certain size and a certain power. I want to talk now about a related type of hypothesis test, but instead now of giving just a binary statement of reject, not reject, it's going to give a numerical value that will reflect the level of agreement between the data outcome and the hypothesis. All right, so let's suppose that we have a hypothesis H, and so I've intentionally omitted some H0 or H1, but let me just consider a single hypothesis, and that predicts a particular distribution for a vector of data. So this could be some multidimensional vector of data. And then you do the observation, and that gives you a single point in data space. Say, here's just symbolically 2 dimensions of the data space. And I observe that point right there. I want to try to come up with a number that reflects the level of compatibility between that observation and the predictions of this hypothesis. All right, so it's not just going to be accept, reject. I want actually a numerical value. So the way to do this is the following, or one way of doing this at least, is you come up with a recipe that would then partition this data space into 2 parts. And on one side, which I've called here omega greater than, I would say that these X values over here are more compatible with the prediction of H. You can imagine that the hypothesis H, maybe it predicts sort of a high probability content here off on the upper right. And here in the lower left, I've called that region omega less than or equal to, and that's the set of X values that are deemed by the analyst to be less or equally compatible with the predictions of H. And by construction then, let's see, this surface, this boundary runs through the observed point. It includes the observed point, and that's considered, the boundary is considered to be part of the less or equal part, omega less than or equal to. Right. Now, there's some subtleties involved here in saying, what does it mean for this point over here in the lower left to be less or equally compatible with H? How can I give meaning to that statement? That's a subtle point. What I'll just say is that in order to say that a point over here on the lower left is less compatible with H, what you have to have in mind is that that same point is more compatible with some alternative. So although I haven't explicitly named an alternative to H, some H prime, I do have in mind, I have to have in mind some alternative in order to give meaning to the statement that the points here on the lower left are less compatible with H. That has to mean more compatible with some alternative. All right, so the analyst has to be able to supply such a rule. It is certainly not unique, and it will depend on the analyst's view of what constitutes less compatible or more compatible with H. And furthermore, it can't just be for this observed point. There has to be a rule that tells you how you would draw the boundary for any observed point. Right, so once you've been able to concoct such a boundary, right, and you have a rule that would create such a boundary for any observed point, then you can give what is called the p-value of the hypothesis. And this is a single number that expresses the level of compatibility between the data that you observed and the hypothesis. Sometimes that corresponds to what we call goodness of fit. In other cases, we'll just, maybe that label is less appropriate and we'll just call it the p-value. And this p-value is the following. It is the probability under the assumption of this hypothesis H to find the data in that less than or equal side. All right, so it's the probability under the assumption of H to find X, let me go back, over here. All right, and remember that that lower left portion includes the boundary. So let me try to put this in words. It's a little bit difficult. It's equal to the probability under the assumption of H to observe data with equal or lesser compatibility with H relative to the data that we got. God, it's hard to, I ran out of breath in that sentence. Let me try again. It's the probability under the assumption of H to observe data as discrepant with H as the data we got, or more so. All right, it's quite difficult, I find, to formulate that in words, but that's the basic idea. The basic idea is that if you get a very small number for this p-value, then that means that there's only a very small probability to find data as bizarre as the data that you found, or more so. And so what you would say then is that that hypothesis is disfavored by the data, right? Because after all, there would just be only a very small probability to find data as discrepant or even more so. And then the way that this is usually treated is the following, is that if this p-value is found below a certain user-defined threshold, alpha, right, for example, 5%, then what you would do is you would reject the hypothesis. You could then also make a binary statement, and this would then be equivalent to the hypothesis test as discussed previously. I'll describe that in a bit more detail in just a second. All right, so that's a p-value. Now, the first warning that we need about the p-value is the following, is that it's not the same as the probability of the hypothesis. It's not the same as the probability that the hypothesis H is true. Remember that in frequent statistics, we don't even necessarily talk about the probability of the hypothesis unless the hypothesis reflects a label for a repeatable observation. And so you might be thinking, well, how about if I were Bayesian? Then I can talk about the probability of the hypothesis. Then maybe the p-values is like the probability of the hypothesis. No, still wrong, all right? If you're a Bayesian and you want to talk about the probability of the hypothesis, then you have to use Bayes' theorem. You would say that the probability of the hypothesis given the data X would be found from the P of X given the hypothesis times the prior probability for the hypothesis. So even a Bayesian would need a prior probability for the hypothesis. All right, and so this p-value does not involve a prior. So for now, we're just going to stick with the frequentist approach. Let's discuss what to do with p-values. So that p-value, that number is the result. It does indeed reflect the level of compatibility between the data and the hypothesis, but it's not the same thing as the probability that the hypothesis is true. It's regrettably easy to misinterpret as that. All right, so here's a simple example. Let's suppose that we have a bunch of nuclei, and we know that they come in only two possible isotopes. And one has a mean lifetime of 0.2 seconds, and one has a mean lifetime of 1 second. Now, that means that for either type of nucleus, you expect the decay time to follow this exponential decay law, but then the appropriate value of tau will depend on which of the two isotopes the nucleus is of. Right? And now you look at an individual nucleus and you measure its decay time, and you find 0.6 seconds. Right? What we can do now is compute, for example, the p-value of the hypothesis that the nucleus was of type, the type characterized by 0.2 seconds. So we've observed 0.6 seconds, and I want to compute the p-value of the hypothesis that it's of, let's call that type 1, all right, the type that has 0.2 seconds for the mean. Well, I have to then decide what is the region of the data space that would give me even less compatibility with my observed value of 0.6. So if you look at the plot here, the sketch shows the exponential distribution with 0.2 seconds in black. All right, that's the hypothesis whose p-value I'm trying to compute. And then in red, the 1 second mean decay time. And I've observed 0.6. And you might say, well, that's a bit incompatible with 0.2. What would be even less compatible? Well, less compatible with 0.2 in the sense of more compatible with a longer decay time, that would be the probability to find t greater than or equal to the observed time. Right? So because the relevant alternative here has a longer lifetime, I say that having t greater than the observed time corresponds lesser compatibility with 0.2, hence greater compatibility with the relevant alternative. So that motivates which way I choose the inequality here for my p-value. And I would then say that the p-value of this hypothesis is the probability under the assumption of 0.2 seconds to find t greater than or equal to the observed time, which was 0.6, and that's 0.0498 seconds. So that's getting to be around the level where you would say that that hypothesis of 0.2 seconds is significantly disfavored. All right. On the other hand, you can imagine, suppose the relevant alternative had not been 1 second, but 1/10 of a second. All right, suppose those are the only two possibilities, namely having 0.2 seconds or 0.1 second for the mean lifetime. So the two isotopes correspond to those two means, and you observe 0.6. Well, then you would say that it's very compatible with the 0.2 value, because you would then choose the region of equal or lesser compatibility to be the other way around, and you would then get a very high p-value. So that's just to illustrate that the definition of the p-value could be different under different circumstances. All right, I hope that made sense. I'm making a mess here. Let me erase that. All right, now let me, in that particular example, the measured data was just a single number, a decay time. But in general, we're going to have some collection of numbers that constitute the output of our measurement. So here I've just symbolically sketched, say, two components, xi versus xj. And so this is the same sketch as before. How do I mathematically describe this boundary that divides the two regions? Well, a surface in a multidimensional space, of course, is described by specifying a scalar function of that vector variable x and setting that equal to some constant. And I want the function to, that constant has to be defined such that the observed point is included in the boundary. So what I would do is I would simply, if I evaluate that scalar function with the observed point, whatever constant value that is, I'll call that t observed. That gives me then the constant. So t of x equals t observed. That is the mathematical equation that describes this boundary. And then this region of less or equal compatibility is the region where t of x is one or the other side of t observed. And let me take that to be greater than or equal to t observed. So I'll define this function t such that greater values correspond to decreasing compatibility, lesser compatibility. And if I do that, then the p-value of my hypothesis is simply the probability under assumption of that hypothesis to find the statistic t greater than or equal to the value of t that I observed. And that, of course, is equivalent. So I can view that as an integral over t, or I can say that it's the integral over the x space, the corresponding x space. It's the probability to find x in the region where t of x is greater than or equal to t observed. All right, so that tells you how to find a p-value when you have a multidimensional problem. And I define the boundary of this region of equal or lesser compatibility using some test statistic. All right. Now, let me make a few more comments on the distribution of the p-value. Now, the number that we get for the p-value depends on where the data point lands. So the p-value is a function of the data. It's a function of a random variable, and therefore it is itself a random variable, and so it would have some distribution, right? If you repeat the observation under the assumption of h, the p-value would have some distribution. What is that distribution? Well, the defining equation for the p-value is the following: is that you integrate over the data space over this equal or lesser compatibility area. That we just said was the integral from t to infinity of the PDF of t. All right. We can then, from that equation, work out the PDF of the p-value. So the defining equation would be that let me call that PDF of the p-value g of p. And we would say that g of p dp has to be equal to f of t dt. And so if I just take that and rewrite it, I can say that the PDF of p is equal to the PDF of t divided by this derivative dp by dt. And then if you go up here and you differentiate this equation, both sides with respect to t, there you can see that because I'm differentiating with respect to the limit of the integral, it just gives me back the integrand. And so this just gives me f of t over f of t, which is 1. And that goes then from 0 to 1. So that's interesting. That tells me that the PDF of the p-value itself is just a uniform distribution between 0 and 1. Right? That's the PDF of the p-value for h under assumption of h. So if you imagine, I don't know, maybe in a Monte Carlo program, always generating data according to this hypothesis h, and then you compute the p-value of h, enter that into a histogram, that would be a uniform distribution between 0 and 1. On the other hand, if you generated the data according to some other hypothesis, say h prime, then what happens is that you would more frequently land in this region of lesser compatibility, right? Because that is to say, it would be lesser compatibility with h would be greater compatibility with h1. So if you generate the data according to the alternative, sorry, h prime, then you're more likely to be in this region of the low p-value. Let me go back. It's easy. You can see that if you generate the data according to, say, some h prime, then you're more likely to be over here, say, because less compatible with h means more compatible with h prime. And so the boundary would get drawn to include that point. And then the p-value would be this area over here, which would be smaller. Right? So therefore, you would more likely get p-values that follow this type of a distribution. It would be peaked at lower values. All right, good. Let's keep going. So what can we do with that? That means the following. It means that if I ask for the probability to find the p-value of some hypothesis h0 less than a specified constant alpha, what would that be? Well, so we've just worked out that the PDF of the p-value is a uniform distribution. And so if I consider some fixed value alpha, then the probability to be less than or equal to alpha is just 1 times alpha. So that's just alpha. And you will recognize that as the defining property of a critical region. So what we can do is the following: is we can use the p-value in order to define a critical region. I can simply say that a critical region of a test of h0 with size alpha is the set of data space where the p-value is less than alpha. All right, so there's this important connection between the first type of hypothesis test that we talked about with a critical region of a certain size, and then the second type of hypothesis test where we found a p-value. We can connect the two by saying you can use a p-value to determine a critical region. It's simply the region of data space where the p-value is less than or equal to alpha. And that resulting critical region, even though we might have set up the p-value without thinking too carefully about an alternative, the resulting critical region will have a certain power. with respect to any given alternative. All right, I hope that made sense. Let's go on and do an example. And this is probably the most relevant example for particle physics. It's what I'll call the Poisson counting experiment. So let's suppose that we observe a certain number of events and we just count them. So the data outcome of the observation is my counted number of events. And let's suppose that these events could be of two different types, signal or background. But you don't count individually. You don't know whether an event a priori is a signal event or a background event. You're just going to count the total. And so let me assume that this number n follows a Poisson distribution where the mean is equal to s plus b, where s is the mean number of signal events, expected number of signal events, b is the mean number of background events, but I can't distinguish between the two. I can just count the total. So you can see what enters here into this Poisson probability is just the sum, s plus b. Let's suppose in this game that the expected number of background events is known. At least let's start by assuming that b is known. And what I want to do is I want to make some inference about s, the mean number of signal events. And so, for example, I could want to test the hypothesis that s is equal to 0. And so then if I can reject that hypothesis, that would be the moral equivalent of discovering the signal process. Of course, before you really say that you've discovered the signal process, there would be many other aspects of this that you might want to consider, the physical plausibility of the signal model and so forth. But from a statistics standpoint, rejecting the hypothesis that s is equal to 0 in a test of a sufficiently small size, that's the step that you need to take in order to say that you have discovered the signal process. And then beyond that, even if you don't discover the signal process, you can test non-zero values of s in order to say which values of s are still compatible with your observation, which values of s are perhaps incompatible with your observation. And for both of these cases, both for testing non-zero values and s equals 0, we need to ask what is the relevant alternative hypothesis. So let's start by considering the following example. Let's suppose that b is equal to 0.5, and we'll take that as known. Now you do the experiment and suppose you find 5 events. Now already you're thinking that doesn't seem very compatible. There must have been maybe some signal process present that explains why I have observed so many events where I only expect 0.5 as my expected number of background events. So do you run off and write a paper where you claim discovery? And if so, how do you quantify the level of significance of this excess? So what you do is you give the p-value of the hypothesis that s is equal to 0. And so we then have to ask, what is the region of data space that is equal or less compatible with our observation under the assumption of s equals 0? Well, the alternative to s equals 0 in this game is some large value of s. So in other words, if the alternative that I want to consider is that the signal could be present, and that would give me typically more events. And so that motivates where I put my region of equal or lesser compatibility. It's having 5 events or more. And so the p-value of the s equals 0 hypothesis would be taken as the probability under the assumption of s equals 0 and b equals 0.5 to find the number of events greater than or equal to the number that I observed, 5. And if you calculate that sum of Poisson probabilities, that gives you a certain quite small number of 1.7 times 10 to the minus 4. Here I've illustrated that. This is the Poisson distribution for a mean of 0.5. So there you can see sometimes you get 0, sometimes you expect to get 1. To find 5 or more, that probability is very low. All right, so there's your low number. And I remind you that that's not the same as the probability that s is equal to 0, right? It's just a different number. So very often in particle physics, we would convert that number into an equivalent value, sometimes called the significance or the Gaussian significance. And it is defined according to the following recipe. In this case, what you would do is the following: is you take a Gaussian distribution and you come up some number of standard deviations, say Z standard deviations, such that the upper tail area, so just in one direction, is equal to the p-value that you got. So that's just a mapping of some number Z onto this p-value. Is just an equivalent number. And there's also, by the way, a two-tailed version of this, but in this particular case, we would use the one-tailed version. And so that means that the p-value is equal to, let's see, the integral of the distribution from minus infinity up to that point. That's the cumulative distribution. And for the Gaussian, there's a notation that we use for that, which is phi of Z. And so here the p-value is 1 minus that, because it's the upper tail area. So that would be the formula. So the p-value is equal to 1 minus capital phi of Z. So capital phi of Z is just 1 minus that integral. And so you can then solve that for Z if you have access to the inverse function of the cumulative distribution. It's just phi inverse of 1 minus p. So these functions phi and phi inverse are available in the widely used computer libraries that we all use in root. Here's the code. It uses Freck and norm quantile. This inverse of a cumulative distribution, that's what's called a quantile. All right, so this is the normal quantile. And in Python, instead, let's see, it's the what's called the survival function, SF. And so that number that you get for the significance, the thing that I call Z, gives you the number of sigmas that you have to go in a Gaussian, such that that upper tail area is equal to the p-value. Now, don't get confused into thinking if I quote a certain number of sigmas and I say that that's sigmas of a Gaussian, I'm not saying that the measurement that I made was a Gaussian distributed measurement. No, in this case, it was a Poisson distributed measurement. It's just an equivalent mapping of this p-value onto a number of sigmas of a Gaussian. Makes it just somewhat more intuitive to understand. And so in this particular example that we just worked out, that p-value of 1.7 times 10 to the minus 4, that gave a significance of 3.6. So you would say that that was a 3.6 sigma effect. So is that enough to claim a discovery? Very often in particle physics, we would claim a discovery if you find a significance of 5 or more. That corresponds to a p-value very low of just 2.9 times 10 to the minus 7. In practice, we might want to revisit that tradition, that the reason that we insist on traditionally on such a high threshold has a number of reasons. It has to do with the fact that we might not trust the model that was used as the basis of computing that p-value. So there could be systematic uncertainties that we don't cover. There could be problems with what is called the look elsewhere effect. That is to say, we might have made many different tests of the same hypothesis. So there's this so-called multiple testing. It could be used to try to cover up all sorts of possible problems, but the p-value is really only supposed to answer a very specific question, namely the probability under the assumption of that hypothesis to find data as discrepant as what we found or more so. So in any case, the tradition in particle physics nevertheless has been to use the word discovery in the title of your paper if the significance is at least 5. Now, I see that we're up to the top of the hour, and so even though I haven't gotten as far as I wanted, I got almost as far. So I propose that we break here for today, and what we'll do is I will continue tomorrow with confidence intervals. And so these will tell you what to do when you test, say, non-zero values of the parameter S. We'll start off by defining that in a more general way. But because we're up to the top of the hour, I propose that we break here. And I hope, Albert, that there is still a minute or two to take some urgent questions.
Oh, yes, we still have some time for questions. First of all, thanks a lot again for another nice lecture, which was very instructive. And there were already a few questions on the chat I saw, but I asked generally if you have a question, And I see one of the chatters raising his hand. So Lucas, go ahead. Lucas, you can ask your question if you like.
Lucas, is it the same question that you
Yeah,
typed in
I
the chat window?
was muted. No, I think you already answered that. Can you go back to slide 20?
20. Yes.
Okay, I was just a bit confused because you said formally the p-value relates only to H0.
Yes.
But I mean, you always have to have the alternative hypothesis, right? To define what is less compatible and what is more compatible.
I've put into the backup slides, maybe I'll skip to this. There were great debates many years ago, and I'm not sure if that means 1920s or 30s, about the role of the alternative hypothesis. And some people, I'm probably going to say the history all wrong here, but this is my rough view of the history, is that Fisher in particular argued that you could say what region of data space was disfavored without reference to an alternative. And what he had in mind was, I think, something like this, that if you looked, suppose you had a PDF for a variable X that was positive, and let's suppose that it had that kind of a PDF. Well, if you just look at that, what does it say? It says X is usually low. It's very rarely high. And so Fisher would look at this and he would say, I don't need to talk about an alternative. Yeah, I can just look at this and tell you that a critical region should be off to the right. Or equivalently, you would say that if you observed a certain value, that you would take your region of equal or lesser compatibility to be off to the right. Do you agree? Good, you're not saying yes.
I don't think so, actually.
Yeah, exactly.
Because I don't agree.
Good. So you've got it right, because others, and I believe it was Neyman and Pearson, said, look, what if the only relevant alternative to H0 was this H1 that I've done there? So then actually you would say that high X is more characteristic of H0.
Yes,
and it's in fact low X, which is more characteristic of the relevant alternative. All right.
Yeah, that's exactly what I was thinking. Yeah.
So that's quite subtle. And I think it's widely recognized that Fisher lost and Neyman and Pearson won. And that in order to say that a certain region of data space is less characteristic of H0, implicitly what you're meaning is that that same X is more characteristic of an alternative. And so that statement therefore will change if you consider a different alternative.
So the p-value always relates also to the alternative hypothesis.
Well, the p-value formally is just defined by this region of equal or lesser compatibility. And,
yes.
And then if you take one step further, you say, well, what does that mean, less compatible? It has to mean more compatible with some alternative. Yes. That being said, very often when people play with p-values, work with p-values, you may or may not explicitly write down the alternative.
Mm-hmm. Okay.
So, for example, very often we might use a statistic like a chi-squared statistic. And so there you would simply say, oh, well, a high chi-squared corresponds to less compatibility, right? You don't necessarily explicitly write down what the alternative is. You just assume that any alternative that gives you a higher chi-squared, that's worse.
Yes, right. And then I have another, maybe it's a stupid question, but could you go to slide 16?
16.
There was basically, it was just Bayes' theorem there. Now, if I want to test an hypothesis that has some continuous variable X, isn't the probability of this continuous variable, I mean, of having exactly this measurement, basically 0? And then you have always 0 on the right-hand side?
No, well, so I mean, here I have some non-zero value for the density.
I mean, isn't the oh, right, it's so I mean the density can be non-zero, but the probability of having exactly this measurement X under the hypothesis H is always 0, isn't it?
That's correct. Now, can I connect that to something else closely related to that? And that is, I came over here and I said, what is the remember we were doing this example with the two distributions for X. It was these two distributions for X. And then at some point in the calculation, I said, suppose I observe the event exactly at X equals 0.1. A posteriori, I can say that's where it came out. What is the probability that this event is a background event? And so then I said that P of B given X is equal to the probability of X given B times the prior probability for B and so forth. And nobody stopped me at that point and said, well, hang on, isn't the probability to have X exactly equal to 0.1, isn't that 0?
Yeah.
Yes. So this is, I think, kind of related to what you're asking about. And so to make this a little bit more correct, perhaps what I should have written is I should have said, consider the probability to find X within some infinitesimal dx of 0.1. All right. And then what I would write here is f of x dx. Do you agree? But then in the denominator, I would also have dx's multiplying each of the two terms in the denominator, and the dx's cancel. So in that regard, you would say, that may or may not have been, I think, related to the point you were driving at.
I think it is. It is related, yes. Okay.
All right, thanks. Mark, I see you put something on the chat on the previous question. Do you want to take something?
I'm gonna deal with Mark's question because this is important, and that is that there could be different conventions in defining what labels you use in this game. And in my book, very unfortunately, which I wrote 23 years ago, I used the opposite convention. But I think that what I was using then was not the commonly used convention, and so I've changed that.
But actually, it seems that the convention of your book is the one of LHC.
Sorry, the convention of the book is what?
Is the correct one. I mean, the one that LHC is using, in my understanding. Yes.
That's not my
If you consider your famous asymptotic paper, it's used for numerator H0.
So H0 is usually just used for the hypothesis that you're testing.
Yes, null hypothesis.
So yes. So sorry, Mark. I see now the issue. The vocabulary that I want to try to stick to is that the null hypothesis H0 is merely a label for the hypothesis that's being tested. Now, in the case of discovery, that means that you're testing the background only hypothesis. But for the case of constructing an upper limit or a confidence interval later, we will test non-zero values of, say, the rate parameter. And so the thing that you regard as H0 could be different depending on the context. And I simply use H0 as a label for the hypothesis being tested. And it's true then that the notation that I've used in my book, unfortunately, departs somewhat from the notation that I've used today. Yeah.
All right, thanks. Mohamed Ali, I think you're next in line with your hand up.
Hi, again, thank you for the great lecture. I just had a possibly not very well formulated question, but when we introduced the test statistics on slide 12, I think it was, I always have trouble with thinking about statistical inference with test statistics because, with test statistics that are dependent on the likelihood, because let's say if we want to talk about a discovery, for example, we would need an observation and then get a p-value from that. Mm-hmm. But the likelihood implicitly have data in them, and I always get confused to what then is that data if it's not the observation.
Well, so the statistic is a function of the data, right? The statistic T is a function of X, and so what you evaluate the likelihoods with the data, with the X that you got.
Yes, but then you build a distribution of these statistics, right? And I believe you do that by generating multiple Monte Carlos, right? And looking at the distribution that comes out. Is that correct?
Yes. And so you could look at so that means, for example, that if you want to know the distribution of T under assumption of H0, that means that you would generate X under assumption of H0, and that for every X value that you get, you would evaluate this likelihood. You would evaluate T.
Yeah.
So
And
I suppose that might seem a little bit unusual. You're evaluating a likelihood for H1, even though the data were generated according to H0, but that's what you do.
mhm, I see. And I guess then, for example, if we take a very kind of trivial example where we assume, a hypothesis, say mass of the Higgs boson being 125 GeVs, right? Then what would, so when you generate X, for example, let's say you're interested in the distribution of, I don't know, invariant mass of the diphotons, right? Which should peak at around 125 GeVs. Would X then have to be individual events rather than the bin distribution, because the bin distribution will almost always look peaked around the mass of the photons?
When you generate the data could be generated on different levels. I could talk about, for example, going back and generating events starting from the hard collision and the parton shower and the detector simulation and reconstruction and so forth, winding up with, say, 2 photons that are my Higgs candidate, and I compute their invariant mass. Other times, when we do just a test of a statistical procedure, we might have some way of parameterizing that mass distribution in some way that skips the earlier steps.
Mhm.
But I'm not sure. So I'm not sure if I'm getting at the core of your question.
Yeah, you are. So
Okay, so sometimes you generate the events starting from the very original process. It might also be, though, that on the basis of those detailed Monte Carlo studies, I might know what the mass distribution looks like under different hypotheses for different Higgs masses, for example, or for a Higgs of a given mass with a given rate parameter. And so, or in particular, for example, you might be able to use your detailed Monte Carlo to generate distributions of some kinematic variables for the background process and for the signal process. And so then you could then pick an arbitrary admixture of signal and background. And so therefore know what the distribution of the kinematic variables would be.
yeah, okay. And sorry, do I have time for just another?
Go ahead.
Right, so that might touch a bit as well on last lecture on the MLE. So when you generate this data given a hypothesis, I've seen it often, we use the likelihood ratio where we have, some mu parameter or parameter of interest in the numerator and the best fit parameter value in the numerator. And this is to construct that test statistic. And I guess my question is, if I've generated my data given using a hypothesis mu, isn't that by definition going to give me a best fit value that is that mu? So that ratio, I'm not sure how the ratio would not give 1 in a way.
No, so the point is that when you generate data, then you have statistical fluctuations, and you can imagine that if you generate data under the assumption of a given parameter mu, then the MLE for mu hat will depart in general from mu, because the MLE has some statistical spread. It has some variance.
Yeah.
But this type of a likelihood ratio that I think you're referring to is coming up in the next lecture.
Okay.
Might have been in the 4th lecture. No, I'm pretty sure it's tomorrow. So hold that question until tomorrow, and I think I'll describe in greater detail. It is also called a likelihood ratio. It is a slightly different likelihood ratio, and it exploits another theorem, not the Neyman-Pearson lemma, but something called Wilks' theorem. So that's coming up soon.
Yeah, thank you.
All right, we're gonna wrap up soon. I have still 2 questions on the list. These are the only ones which we're still gonna take, so don't ask new questions now. Save them for tomorrow. But first we have Rishabh. You were asking very early on a question in the chat. Is that still relevant and needs to be answered? Did it got answered during the lecture already? And if so,
yes. Can you hear me?
Yeah.
Yeah, I mean, I wanted to know, like, what are some of the variables, like, I guess in slide 11 or before that you were talking about multivariable data, like for instance, X would be a vector. What are some of the examples of xi and xj in practical physics?
Yeah, I think I see your question. I could take this on many different levels. So let's suppose that the objects that I'm examining are individual events. And so the data vector is a collection of numbers that characterizes an individual event. I could take the x sub i's to represent the components of the momentum vector of every particle. All right, then I would have a very high dimensional data space. Or I could form jets out of the particles, and the x sub i's could refer to the momentum vectors of those jets. Or I might just focus on a couple of jets in the event, and I might be interested just in their PT and eta values. Or I might form pairs of jets and look at their invariant mass, and in which case maybe I only have a few values that characterize each event. So, but in any case, the xi's and xj's, those are going to be some measurable numbers that I measure for each event. Maybe PT of a muon or something like that. Hope that makes sense.
Sure, thank you.
Okay, last question for today. Is that the last one at the chat? Maybe you see it, Glenn from Tuan Pham. Maybe something you're going to discuss in the next lecture, so then you can just say so. And
let me just say, are you going to elaborate on the method to obtain the PDF of the when? Good question. So in other words, how do you get this the distribution of the statistic? I had in mind, first of all, that what you've written here in the chat window, and that is that you could simply run the Monte Carlo model for each of the two hypotheses, and in that way look at the distribution of the statistic. And if that's not feasible, then there are a number of approaches that we can take, but they're not going to pertain exactly to the likelihood ratio as I've written it here, but with this other type of a likelihood ratio that I just alluded to, and we're going to be able to use something called Wilks' theorem to write down the PDF of such a statistic. It'll be very closely related to a chi-squared distribution. So that's coming up tomorrow as well.
Great, thanks, Glenn. So there is a question, I think it was more to me, which I will just touch upon, is people asking if there are also lectures of machine learning we can do sometime, not in this series, but another series. Just add a few comments on that. I'm sure that's very interesting to do. And in fact, I did that once, and in the years before COVID. And then, in fact, I found no room big enough at CERN to actually entertain the audience, and by a factor of 2. So it was over popular, let's say. And so we did do that again since then, but there was also the machine learning forum that started, which was picking this up. In the new world, we may think of that for our next year's program to do that. So don't despair. Okay, good. Thanks a lot, Glenn, for this excellent lecture and the explanations and everything you gave. Tomorrow there is more, and we continue same time.
And I look forward to seeing you all tomorrow.
Yeah, so same time, same place in Zoom world. See you tomorrow. Bye.
Bye-bye.